Hey, welcome back. This is Calculus 2, section 8. Oops, it says 4, but it should be 8.3. Let's fix that. And we're talking about trig integrals. So basically I'll begin with kind of every trig identity that you kind of need to know to survive this section. So I'll just call these helpful identities. And some identities I totally take for granted at this point. But I expect you to know kind of the right angle definitions and like they call them reciprocal identities and the quotient identities just very quickly. You might want to fast forward through this if you kind of already know them. Secant tan theta. So sine is opposite over hypotenuse. You can also think of it though as 1 over cosecant, although it doesn't help very much to kind of go in that direction. Usually if you see 1 over cosecant though, you can replace it with sine. We're generally most familiar with sine and cosine, and it's kind of when you're dealing with integrals, you kind of want to transform it into terms of that, and then you can manipulate it easier. But I mean, it's just going to come down to us as humans' experience. Okay, just doing enough of these and getting a good idea of how they work. Okay, anyways, cosine is adjacent over hypotenuse, which is same as 1 all over secant theta. And then tan is the ratio of sine and cosine, right? So it's opposite over, I guess we don't really need the opposite over hypotenuse stuff, but well, there it is, you know. But anyways, there's kind of two identities for tan then, the quotient identity, which is sine theta over cosine theta, and then there's also the tangent identity, the reciprocal identity, 1 over cotan theta, right? Cosecant, of course, is 1 over then sine theta, and of course hypotenuse over opposite. Let's just dispense with those. I'm hoping you already know that. Okay, I hope that you learned that in pre-calc. Secant then is 1 all over cosine, and of course cotan then is cosine over sine, but also then 1 over tan. Okay, so these are things I take for granted. Anything along that level, I'm going to assume, so I assume you are able to, you have the reference angles memorized, you have this chart embedded in your brain somewhere. So where do we start? 0, and then the next bigger angle, pi over 6, and then pi over 4, then pi over 3, then pi over 2. And if you've never seen how to fill in this chart, it's pretty simple and easy to memorize. But what is sine? It's going to go 0, and then in here, and then 1, and then cosine is basically the same thing, but in the other order. And I'll fill in that stuff there here in a second. 0. So sine, to fill out the chart, what you kind of can do is just go 1, 2, 3, and then the bottom is always, 2. And then you take square roots across the top. Okay. Then cosine is just in the reversed order, so it's 3, 2, 1, then 2, 2, 2, square roots across the top. Square root of 1's 1. And then tangent is just the ratio of those. Okay, so I mean root 3 over 3, 1, root 3, and then undefined. So I expect you to have that memorized. Hopefully you already have that. Then there's what they call the Pythagorean identities. You could divide this thing by cosine squared, and you end up with tan squared theta plus 1 equals secant squared theta. if you divide the original identity by cosine squared, you get, by sine squared, then you get 1 plus cotan squared theta equals cosecant squared theta. So those three, but you also have to know kind of, so stuff like sine squared 3 theta plus cosine squared 3 theta is also equal to 1. So this is true for any angle. And then also you need to be able to kind of identify secant squared, stuff like secant squared minus 1, what does that equal? Well, you use that second identity, right? And you just solve for tangent squared. And so there's identities that are kind of related to those 3 Pythagorean identities that hopefully you can, what are some other ones? They call these the half angle identities. 1 minus cosine 2 theta all over 2, and then cosine squared is the 1 plus cosine 2 theta over 2. And then they expect you to kind of, again, know all variations. So if you have sine squared of 3 theta, that'll equal 1 minus cosine of 6 theta all over 2. That sort of idea. Then there's the double angle formula, sine of 2 theta equals 2 sine theta cosine theta. But again, you should be able to handle variations on that theme. For instance, the sine of theta, you can always write as 2 sine of theta over 2, cosine of theta over 2. What else? The even and odd identities will come up every once in a while. So the cosine of negative x is just going to be cosine of x because cosine is even. Sine of negative x will be the negative sine of x, of course, because sine is odd. From there, I expect you to know all the derivatives. So derivative with respect to x of, I guess we always start with sine x, and then derivative with respect to x of cosine x, derivative with respect to x of tan x, and then these other guys. So the derivative sine is, of course, cosine x. Derivative cosine is negative sine x. Derivative tan is secant squared x. Am I recording? Did I even push record here? Oh my gosh, thank gosh. All right. Anyways, then this will be negative cosecant x, cotan x, and then this is positive secant x, tan x, and then this is back to negative cosecant squared x. Okay. And then if you know the derivatives, you should automatically kind of have the integrals. So the integral of cosine x dx, the integral of sine x dx, the integral of secant squared x dx, the integral of cosecant x cotan x dx. I'm going to fill these in a second. The integral of secant x tan x dx, the integral of cosecant squared x dx. So the integral of cosine, of course, is sine. The integral of sine is negative cosine. The integral of cosecant cotan is negative cosecant. This will be positive secant. This will be negative, I guess, cotan. This other guy finally is tan x plus c. So you should know those because you know the derivatives, and these are just the reverse of the derivatives. And then what else? You need to kind of have these other, we wish we could have the integral of tan, just like up here we have the derivative of tan, but there's kind of not that kind of nice circular relationship like there are with the sines and cosines with respect to derivatives. so we wish, we also then had the integral of tan x, which we do. I kind of wanted you to have this one memorized. That would be ln absolute value of secant x plus c, or if you'd rather, negative ln absolute value of cosine x plus c. Those are equivalent. So if you know that one, then it's not too far of a stretch of reality to know cotans. I wouldn't call you out on that though. This would just be ln of absolute value of sine x. Let's see. Then there's the so I would expect you to have that one memorized, right? Not the cotan. So I want to say you don't have to memorize this one. Don't bother. Don't memorize. But integral of then we wish we had the integral of secant x. Above we have the integral of secant squared. This one is one of the funny ones where it had a weird u substitution. It ended up being secant x plus tan x, and this ln, and then plus c. Also wish we would have an integral for cosecant. Right. That turned out to be something like negative ln absolute value of cosecant x plus cotan x plus c. In the tables, sometimes you'll see it as ln absolute value of cosecant x minus cotan x, which is equivalent. Okay, so there's a lot. You should make note cards, if possible. From the last video, we also had secant cubed. Fortunately, I don't remember that one off the top of my head, though, because I'm not going to list it. Excuse me. Sure. Let's move on. Okay. So what you're going to see in the beginning here are it's kind of like a program almost. They kind of build a computer program based on the powers of sine and cosine. So let's say we have sine to some power m, as in I don't know. Mother, m as in mother, and then cosine raised to some power n as in nano. So sine, cosine version, and then there's kind of do this if this. So we'll say if m is odd. Okay. So the way it works is you'll go through kind of this algorithm. You'll push back one factor of sine, and what that does is serve as your when you do your u sub, that will be your differential part. Okay, so you're going to do a u sub on cosine eventually, but before you do that, you're going to convert the remaining signs to cosines, because you're going to have an even number of signs at this point. You can use our Pythagorean identities, right? So cosine squared plus sine squared equals 1, but you can also rewrite that in terms of solving for sine squared, so that would be 1 minus cosine squared. So you can replace all the remaining signs in terms of cosines, and then finally do your u sub for cosine. Okay, so that, I guess this is kind of algorithm part A. Let's take a look at an example of this. Then we have the integral of sine cubed of x, cosine squared of x dx. Okay. So as I said, and what do I mean by push back? I mean kind of factor it backwards. So here we have 3 factors of sine x, so I can kind of borrow 1 factor of sine x and push it to the back of the integral. Okay, so I have a sine x dx right here. Okay. Then I'm going to convert the remaining signs and the cosines using my Pythagorean identity. And that sine then that I kind of factored backwards to the back of the integral, that sine x dx is going to become the differential of the u sub, right? So watch, if I let u equal cosine x du, the differential will be negative sine x dx. So it's almost that. There's just a negative to worry about. It'll make everything negative, basically. But if you want to do it like a computer, you can solve for dx and have du over negative sine x. Okay, so we can do our substitutions then. We'll have 1 minus u squared times sine x times du, negative du over sine x. And then you can kind of multiply this thing by a negative u squared, and you're getting rid of the sign. You can factor the negative out too, but I'm just going to go negative u squared times that if I distributed, and then I'm going to change the order. So I end up with positive u to the fourth minus u squared, because I just like leading coefficients to be positive. It's just the way I was raised. Okay. So the integral of u to the fourth then is u to the fifth over 5. Integral of u squared is u cubed over 3. And then we have a plus c, and then you back sub and you're done. Okay, so you have this weird kind of polynomial in terms of trig functions. Okay. Let's see what else. So that's the first kind of like program that you have to follow. So if m is odd, do that. If n is odd, so you would kind of check them in order. So both of them could potentially be odd, right? You could have sine cubed and then cosine cubed. You could still use this method on that version. Okay? But if it turns out that sine has an even power and cosine is odd, in other words, if n as in nano is odd, then you can follow this program and it'll work. So first push or factor back one factor of cosine x. It's just the reverse process of what you saw above. Convert the remaining cosines to sines. And in this case, you have your Pythagorean identity saying that cosine squared x is equal to 1 minus sine squared x. And then thirdly, do a u sub. So let u equal your sine x in this case. Okay. So basically, the thing that you're factoring backwards will turn into your du. So this thing will equal your du. Okay, we hope. All right, so anyways, let's take a look at an example of that. And here we have the integral of cosine cubed x sine to the fourth x dx. So if you're following this program, m is even, so you would have to go to the second if-then statement. And here, n is odd, so we're using the second procedure. Okay, so first off, we factor back or push back one factor of cosine. Okay. We're going to convert the remaining two factors of cosine into 1 minus sine squared. Okay. Whoops, that's an equivalence there. And then we have 4 factors of sine here, and then cosine x dx. And then do your u sub, so u is sine x, du is cosine x dx. And yeah, that's exactly what we had pushed to the back of the integral. If you want to do it like a computer, though, you can always solve for dx, and you get du over cosine x. So we'll end up the integral of then 1 minus u squared times u to the fourth times cosine x times dx, which is du over cosine x. And you see the cosines are gone. You just have du. So this is, this is du. Okay, let's go ahead and distribute the u to the fourth. Get integral of u to the fourth minus u6 du. And then we can easily integrate that character. U to the fifth all over 5 minus u to the seventh all over 7 plus your integration constant. And this time we end up with a polynomial in terms of sines. Okay? So sine to the fifth x over 5 minus sine to the seventh x over 7 plus c. Okay? So the last one. Well, wait a second. Oh, I screwed up the last one. No wonder. I was thinking, man, I could have swore that's exactly what I did in the last one. I apologize. So this is cosine in both cases. So you get this weird polynomial in terms of cosines. Okay. If it turns out that both m and n are even, there is this weird thing called Wallace's formula that you could play around with. Oh no, wait. Sorry, I'm not there yet. So see in the part of the algorithm, it fails both the above, right? So if n is odd, it tells you what to do. If n is odd, it tells you what to do. But if m and n are even, then it don't really tell you what to do. So in that case, we have this following. If m and n are even, what you want to do is use the half-angle formulas from above. And I'll just remind you what those are. So you have two versions. You have the sine squared version, which is the 1 minus cosine 2x over 2. And then you have the cosine squared version, which is plus 1 plus cosine 2x over 2. So let's maybe look at one of those characters. So we have the integral of cosine to the fourth of 3x dx, something like that, right? So we can convert that into, well, even before we pull any of the formulas out, we can rewrite this as cosine squared dx. And then we can do a substitution for cosine squared, right? So in that case, we would end up with 1 plus cosine, and it actually doubles the angle. Usually you're kind of going in the other direction, so it's a half-angle formula, but in this direction you're doubling the angle, so it'd be cosine 6x all over 2 squared dx. And then you have to literally FOIL that thing out. So you're going to end up with 1 plus 2 cosine of 6x plus cosine squared of 6x all over 2, 4, right, because it's squared, 4 dx. And then we're going to probably want to kind of just rewrite this 1/4 plus 1/2 cosine of 6x plus 1/4 cosine squared of 6x. They may have called this power reduction formulas back in pre-calculus, because what you always want to do is reduce the power. So we reduce the power, this cosine to the fourth, into at least 2 terms that don't have powers, and we can integrate those. But this one still has a power on it, so use it again. Okay, so rewrite this 1/4 plus 1/2 cosine of 6x plus 1/4. This thing will be 1 then plus cosine of 12x all over 2 dx. And that completely reduces the power, right? So power reduction, 1/4 plus 1/2 cosine of 6x plus, that's a 1/8 if you kind of butterfly and then distribute, 1/8 plus 1/8 cosine of 12x. And then probably want to combine some like terms there, so we'll have 3/8 plus 1/2 cosine of 6x plus 1/8 cosine of 12x and then antiderivative. I'm going to dispense with the u subs. I just noticed that this thing is going to give me a factor of 1/6 when I do my u sub, and then this thing will give me a factor of 1/12. Okay, so you end up with 3/8 x plus 1/12, because it's 1/2 times 1/6 sine of 6x, integral of cosine of sine, and then plus 8 times 12 is probably like 96, right? 1/96 sine of 12x, and then plus c. Okay, it's kind of long, but it's very kind of computer programmed. You're just kind of following a list or procedure. Okay, so in cases where you have like just strictly one function, like cosine to the 9th or something like that, or even cosine to the 20th or something like that. There's something called Wallace's formula in there to handle those exceptions. And I'm not going to go into Wallace's formula, but it is really interesting to play around with. But it's going to, in the long run, I'm not really all that interested in it. But if you want to kind of learn something, and it's kind of neat, but well, I'll just show you an example. If you know Wallace's formula, you can do things like this. I'm not going to put this on a test or anything. I just if you know Wallace's formula, believe it or not, this thing turns into pi over 2 times 9/10 times 7/8 times 5/6 times 3/4 times 1/2. Okay, believe it or not. So anyways, I'll leave that to you if you want to go above and beyond the call of duty. Okay, the next section then are integrals of secants and tangents. Okay, and then of course, if you wanted to, you could look at integrals of cosecants and cotans, which will kind of have the same behavior. So anyways, secant to the m as in mother, and then tan to the n as in nanometer. Let's investigate this. And again, we have kind of a procedural, a program, an algorithm, if you will, if m is even. Okay. So in this case, you want to push back either the derivative of secant or the derivative of tan. And the derivative of secant is going to kind of work, because if m is even and you push back two factors of secants, then the resulting exponent on secant will be even as well, and you can convert that into terms of tan. Okay, and then you'll have an integral in terms of tan. You could do a u sub, and the differential will cancel out. So let's explain this a little better. So first, factor back, or push back if you'd rather, factor back secant squared x for your differential part, and then secondly, convert your remaining secants to tans using your Pythagorean formula. So secant squared x, is 1 plus tan squared x. And then thirdly, let u be equal to your tan. Okay, so let's go through one of these characters. Example, secant to the 6 4x, tan of just plain old 4x. So the degree on tangent is just 1, and then dx. Okay, so an even number of secants there, we can factor back 1 secant squared. We'll be left with 4 secants, 4 factors of secants, and then tan of 4x, and then there's that secant squared of 4x that we pushed back, dx. Okay, and you see this part will become your differential and your u sub. Okay, so next we want to convert the secant to the 4th and the tans. So we know, secant to the 4th is really secant squared squared. So we're going to end up with secant squared squared, and then we could replace secant squared with 1 plus tan squared. So hopefully that makes sense. And then you have tan, and this should be 4x, and then you have tan 4x and secant squared 4x sitting here at the back. At the end of the integral. So non-English speakers sometimes read from right to left, so I don't want to see back. So it's just the end for us, I guess. I don't know. Anyways, let's go ahead and do our u sub. So our u, we're going to let be tan x, and then our differential, and I keep forgetting it's tan 4x, and then our differential is secant squared of 4x times 4, because of the chain rule, and then dx, and then we could divide out by this 4 secant squared 4x, and you see that it's going to cancel out with all that material. There's a factor 1/4 we have to deal with, but we'll just factor that out. So anyways, I got 1 plus now u squared times u times secant squared 4x times dx, which is du all over 4 secant squared 4x. And we have a nice cancellation, factor out the 1/4 of the integral of then 1 plus 2u squared plus u to the 4th times u times du, and then you can distribute the u and get 1/4 the integral of u plus 2u cubed plus u to the 5th du, and then we can do power rules on all that material. So we'll end up with 1/4 times u squared over 2 plus 2u to the 4th over 2, which would be 2u to the 4th over 4, which would be u to the 4th over 2 again, plus u to the 6th over u, or over 6, and plus c. And then you're back subbing, and you get this weird polynomial in terms of tangents, right? So we'll have then tan to the 2nd power of 4x all over 8 plus tan to the 4th power of 4x all over 8 plus tan to the 6th power of 4x all over 24, and then plus c. Okay, so that's one program. The other program is then if your n is odd, you can always kind of default to this other method. Okay, so there's sometimes 2 ways to do the method. If it was a computer, you would just, go through the if-thens in order, but us humans, you have a choice. You can literally do one way or the other, and usually it's just kind of common sense. If you don't do it right, it's not going to work. You're not going to get your nice cancellations to happen, so you'll try something else. By no means do I, as a human, memorize these procedures. I'm more of the kind of get my feet wet and play around with it, and through doing homework, it's more of the I don't know, the neural network computing than sort of this if-then coding type universe. So anyways, the other case then, like I said, it is when n is odd. In those cases, then you can push back a factor of sine, a secant, and a factor of tan for the derivative of your u sub. So push back a secant tan. Then you're going to be converting everything into secants, right? So convert the remaining tan into secants using your Pythagorean identity. So tan squared x is equal to secant squared x minus 1. Thirdly, then let your u equal what? U equal secant. Okay. Let's make this question the quiz question for this section. Okay, so let me mark that down in my notes so I don't forget. Oh boy, where are my notes? This is the quiz question. This is the quiz question. This is part of homework, video homework number 4, I believe. This is 8.3, and I'm looking at this integral. Sorry, just one second. Tan cubed 2t secant cubed 2t dt. Okie dokie. Let's take a look. So here we go. Example, integral of tan cubed 2t secant cubed 2t dt. And first we're going to push back a tan secant. So it'll leave us with tan squared 2t, secant squared 2t, and then tan 2t secant 2t dt. And then we're converting the leftovers to secants. So we'll have secant squared 2t minus 1 times secant squared 2t times, let me rewrite the secant in front. We're used to seeing it like that. Tan 2t dt. And then u sub for secant 2t. And then we have a du is secant 2t tan 2t, chain rule, there's a 2 out in front. Okay. So that's the stuff we pushed back right here. And then dt, of course, we have du over 2 secant 2t tan 2t. And what we'll end up with then is u squared minus 1 times u squared times secant 2t tan 2t times du over 2 secant 2t tan 2t. And you don't have to write all that beeswax out. You could just, put the 1/2 in there and remove the secant t tan 2t. If you get a little better at doing the integrals, if you have more confidence than I do. U to the 4th minus u squared du. And then power rule it, so you get u to the 5th over 5 minus u cubed over 3 plus c, and then you end up with a weird polynomial in terms of secants. So secant 2t, I'll just write the 5th on the power on the outside, minus secant 2t cubed over 3 plus c. Okay. Finally, one case that also will come up then is the case where you have just tan by itself, where the exponent is even. And in those cases, you want to reduce the sign, reduce the exponent using the Pythagorean identity and then kind of expand it. So reduce by converting tan squared into secant squares minus 1. Okay, so let's take a look-see at one of those characters. And we'll actually do one where we evaluate the expression. So 0 to the pi over 4, and we're dealing with tan to the 4th x dx. Okay, so our integral, we're going to rewrite it as secant squared minus 1, secant squared x minus 1 times tan squared. Right? Because this thing is really just tan squared, and then if you go tan squared times tan squared, you get back to tan to the 4th. Okay. So we can do that. All right, so what? Well, now I can distribute like that and like that, and I'll end up with the integral of tan squared x secant squared x dx minus the integral of tan squared x dx. Okay. I can do a u sub on tan for this first integral. So let me let u equal tan x. And then the differential is sitting right here. You know, the derivative of tan is just secant squared x dx. So that's du. So that first integral will become, and I'm not going to bother with the replacing dx with du over secant squared x. Sometimes gets a bit silly doing that. Tan squared x, whoops, I'm replacing tan with u, so I end up with what? U squared du then. Right. And then the second integral, you're going to reduce that again into secant squared x minus 1, because we know the derivative of secant squared. So the first integral then will become u cubed over 3, and then we'll have, you know, I guess we can do these integrals here. So the integral of secant squared is just tan. Oops. I'll be a little careful with the distribution of the negative, and then plus x. And then back sub, and you're ending with a kind of a weird mixture of a polynomial in terms of tan with the variable x. Okay. You know, it's unusual that you get these weird kind of polynomials, but if you know more about the theory, I think it's related to the fact that there's kind of groups of functions that kind of form a structure, without a better way of saying it. It kind of goes back to what I was saying about, you know, if you have two integers and you add them together, you just end up with another integer. So you get -3, -2, -1, 0, 2, 3. Okay. So if you add like -3 to 1, you end up with +2. So imagine like a set of things like that, except their functions. Let's call it S. And inside that set of things, you would have stuff like x, sine x, tan x, and the operations you kind of do with them are to form polynomials with them. You can exponentiate them. You can take logarithms of them. You can put them into polynomials so long as they're kind of algebraic polynomials. And when what you do is you kind of produce a universe from this set, a universe of functions, and the universe then kind of look like things like this, like these polynomials in terms of trig functions and stuff like that. So you're going to get polynomials in here. You're going to get trig functions, rational things, so ratios of things over things. And then when you're taking derivatives and integrals of them, they kind of just stay in the same set. So like up here, when you're adding two numbers together, you just get another number. And the S set, whenever you take integrals or derivatives of these things, you kind of just get another thing that's within here. So the outputs of your integrals, there's not really, you know, it's not unknown territory here. It's kind of like after a while, hopefully you become familiar with it like you would become familiar with the integers like in grade school. Okay, it's just you're kind of entering a different universe that has a different kind of structure. It's infinite, sure, but it's not, you know, unimaginable, I guess is what I'm trying to say. Okay. Anyways, let's move on to kind of look at maybe one that's kind of a none of the above situation. And what we've tried to do is give you kind of an algorithm that will work in most circumstances, but not all computer programs work, right? So what are some things you could do? You can try to use some reduction formula from the back of the book, basically, or you could try, what I like to do is always try converting things into more familiar forms. So try converting into sines and cosines. Okay, so an example of that might be something like the integral of 1 over secant x tan x, okay, dx. So certainly this thing, you know, as it sits, may look kind of foreign, but if you were to rewrite it in terms of sines and cosines, what would you get? Well, first off, you could rewrite it as kind of 1 over secant x times 1 over tan x. And that's not even a trig identity. That's just more of a fact, about factoring expressions from basic arithmetic. So you can then rewrite these things, right? So secant is what? Well, that's 1 all over cosine. Or if you just write 1 over secant is equal to cosine, it's a little more direct, right? So let's just do that. And then 1 over tan is just equal to cotan. But even this isn't very familiar. So what I would suggest doing is then rewrite the cotan as cosine over sine. Okay. And maybe that's not all that familiar, but it's going to get you closer to your goal. So it will take a bit of thinking, right? You kind of look at it and what are you familiar with? Cosine squared, is the same as 1 minus sine squared. And then you could bifurcate this thing or butterfly it into 2 fractions. But it really, for us humans, it comes down to a matter of experience and just doing homework. And this will be sine squared x over sine. And spending lots of time with mathematics. Okay? You kind of have to sacrifice part of your life for math. As social human beings, it's hard to do if you're a social person. If you're not social and you don't have a lot of friends, it's still hard, but maybe a little easier in those cases. So anyways, 1 over sine x is, well, I guess we kind of got back to where we started there. No, we didn't. 1 over sine x is cosecant x. Sine squared over sine is just sine x. Both of those are known. The first one's probably not all that familiar, the cosecant one. Of course, that's just negative ln absolute value cosecant x plus cotan x. And then the integral of negative sine x just give you plus cosine x. Okay. See, and of course, I had mentioned above that this is equivalent to cosecant x minus cotan x plus cosine x plus c, using power rule for logarithms and some clever identities. So anyways, that's pretty much the big and the small of the trig material. So there's program. This would be easy to get a computer to do, right? I think in practice, you have this for reference. You have my notes for reference, but in general, you do enough of them that you kind of get experience, and then you're like, ooh, I kind of know what to do. I got to push something back so it's the derivative of my u sub and all that jazz. And hopefully, for me at least, this kind of stuff was like riding a bike. I get in there and I do it a couple times, and it was pretty easy. The next section, you're going to see a technique that is not like that. It's not like riding a bike, and it's something you're going to have to look up probably in the future to remember how to do it. But anyways, the last section I just wanted to note was the product sum formula. This is something that I will not be putting on the test because people generally don't have these formulas as well encoded as the other ones. But basically it's for handling sort of cosine, sine, cosine, sine, and your integrand where you have different angles. Okay, so maybe you have something like cosine mx times cosine nx. And so you do a product sum formula. I call this a couscous formula, but it will be cosine of m minus nx plus, it's been so long since I've used it, there's 1/2 in front. I kind of forget how it goes as well. But then plus cosine of m plus n x. Like I said, I wouldn't put this one on the test, but it's in there, and who knows? You never know. Okay. So the story I always tell is about me in grad school. I got into my first year of my PhD program in math, and the teacher was kind of like, well, if you can figure out this one problem, you can keep your scholarship. If you can't, goodbye. And he gave me an integral, okay, a very hard integral. And I did tons of work on it. You know, I stayed up night and day trying to figure it out. And eventually, I couldn't do it. You know, and my first instinct was that it just wasn't doable. And I go into his office, you know, and I say, oh, I just can't do it. And he tells me he actually made a mistake when he wrote the test. So the test, and at that point, there's like 5 questions, and you pick one. So anyways, that question, he had made a mistake in it, and the integral there wasn't doable. So I was right, but I didn't have the courage to say it. And basically, I lost my scholarship there and had to go back and become a substitute teacher for $12,000 a year. Really wouldn't even let me teach math classes. I was teaching, you know, gym class and a lot of remedial classes. They loved using me in developmental ed, which was fine with me because a lot of those developmental ed kids were a lot nicer than some of the other students. But anyways, the moral is you never know. Okay, you never know what in your degree program is going to be kind of important, and so I'm just trying to cover all my bases, I guess, and I hope you never have to go through what I did. So, anyways, here I converted cosine 2x, cosine 6x into a sum of 2 cosines that now I can take the integral of, right? How did I get cosine -4? Well, that's just 2 minus 6, right? I'm just using this formula that's given in the book. There's like 4 of these. Okay, this is just one of them. And then I have 2 plus 6 is going to be 8 here. Then you could use the fact that cosine is even to rewrite cosine of -4x as cosine 4x, and then plus cosine 8x, and both of those are easily integrable. So you end up with 1/2 times, and there's a u sub in there that I'll just omit, 1/4 sine of 4x plus 1/2 times 1/8 sine of 8x, and then plus your integration constant. Okay. This will be 1/8 sine of 4x plus 1/16 sine of 8x. Let's see. Another story that when I was at Akron, I had a British teacher, and he said he knew somebody in World War II where he was I guess in Germany, and the Nazis were, you know, at that time searching for people and just murdering them. And this guy that was in Germany, he was a mathematician, and the Germans caught him, and they were just going to shoot him, and, you know, and kill him. And he said, no, wait, I'm a mathematician. And the Nazi said, well, prove it, you know, do an integral in the dirt here so I can see that you're a mathematician. And of course he was able to do the integral, and he lived. So being able to do an integral, it could keep you in a program, a college program. Like for me, maybe I could have stayed in the PhD program if I had gotten that integral. But it can also save your life. You kind of never know what's gonna pay off in the end. So just, you know, keep on studying and keep on trying, and the stuff it pays off. Okay. So that's the end of my shtick, and I will see you next time.